Earth provides a familiar reference because it can be measured directly with many independent methods. Its shape is close to a sphere, slightly flattened at the poles by rotation. The most useful starting measure is its size across the distance from one side to the other through the centre. That diameter is a little over 12,000 kilometres. From this single number, many everyday scales follow. If a person travels a few kilometres, the ground appears flat because the curvature is small over short distances. If a person travels hundreds of kilometres, the curvature becomes measurable with careful instruments and with long lines of sight. If a person travels around the planet, the path closes on itself after a distance of about 40,000 kilometres along the equator. These are not abstract facts. They are the basis for navigation mapping and the way the horizon looks from a ship or a high building. The surface area of Earth is large enough to hold oceans, continents, and an atmosphere that varies in thickness and composition with height. The atmosphere is thin compared with the planet's radius. Most of its mass lies within a few tens of kilometres of the surface. Even the altitude where many satellites orbit is small compared with Earth's size. When a spacecraft rises to a height of a few hundred kilometres, it is still close to the planet in a geometric sense. The planet fills a large fraction of the sky, and the curvature becomes obvious. This is the first shift in perspective that helps a mind accept large scale. It shows that what seems vast on the ground becomes a thin layer when viewed from above. Earth's gravity sets a physical boundary for many practical definitions of near space. Objects orbit because they are in free fall around the planet. An orbit is not a place where gravity stops. Gravity is still strong. The orbit exists because the object's sideways speed makes it fall around the planet rather than straight down. The most common low orbits circle Earth in roughly 90 minutes. That period is a timing marker tied to distance and gravity. A longer orbit period means a higher orbit. A geostationary orbit, where a satellite appears to hover over one point on the equator, has a period equal to Earth's rotation, so it sits far higher at tens of thousands of kilometres from the surface. Even that is still close compared with the distances that follow. The Moon is the next useful step outward because it is the nearest large body and can be used to calibrate distance. The average distance to the Moon is about 380,000 kilometres. This number is large compared with Earth's diameter, yet it is small compared with the span to the Sun. A light signal takes a little over 1 second to travel from Earth to the Moon. That time delay is a direct physical expression of distance. The Moon's orbit around Earth takes about a month, and the changing angles between Sun, Earth and Moon produce phases. These cycles are a human-scale bridge. They show that even the nearest neighbour is far enough that travel takes days with chemical rockets, yet close enough to be reached in a single mission, without needing years. Between Earth and the Moon is a volume of space that is mostly empty. It contains sparse gas dust and magnetic and particle environments shaped by Earth and the Sun. This emptiness is also part of scale. When people imagine space, they sometimes imagine a filled medium. In reality, the region between planets and moons is closer to a near vacuum than to any terrestrial environment. It matters because it means distances do not come with continuous scenery. In a spacecraft, the view is dominated by bright points and blackness, and the sense of motion is not reinforced by nearby objects. Scale becomes a matter of instruments, time delays and changing angles. Earth's location within the solar system is already far from the centre in a common mental picture. The Sun is the dominant mass, but Earth's orbit is one of many. Earth travels around the Sun at a speed of tens of kilometres per second. The orbit takes 1 year. This motion is smooth and stable. It is so stable that it defines calendars. Yet when Earth is used as the base unit, the orbit is enormous. The radius of Earth's orbit is about 150 million kilometres. This distance is called an astronomical unit. The unit is useful because it is the first scale jump from the Earth-Moon system to the broader solar system. In Earth diameters, the astronomical unit is more than 10,000 Earth diameters. In moon distances, it is almost 400. The numbers show how quickly scale expands when the reference shifts outward. Even at this stage, the farthest light in the title is not approached. The purpose is to build a stable ladder of size starting from what can be held in mind. Earth is the first rung. The planet's diameter and circumference create a ground truth. The thickness of the atmosphere and the height of common orbits show how thin the living layer is relative to the whole. The Moon's distance shows the first large gap that can be crossed with technology, and the emptiness between bodies shows how space is not packed with intermediate landmarks. Earth itself is also a moving point in larger reference frames. The planet rotates once per day and orbits the Sun once per year. The solar system itself moves through the galaxy. These motions will become relevant later, but here they are held back. At this point, the only purpose is to establish what a planet is in dimensions and what it means to step away from it. The shift from ground to orbit, from orbit to the Moon, and from the Moon to the definition of the astronomical unit forms a foundation. It offers a way to translate later numbers into a pattern. Each step outward multiplies distance by factors that quickly exceed ordinary intuition. Earth's scale is therefore a disciplined starting place. It is large enough to be a world, yet small enough to be measured. It is the unit from which the rest of the universe will be unfolded one region at a time, without jumping ahead, until the farthest light becomes a boundary defined by travel-time expansion and the limits of what can ever reach an observer. From Earth as a measured sphere and the Moon as the nearest major distance, the next region is the planetary neighbourhood of the inner solar system. This region is defined by the space where rocky planets and their orbits set the main structure, and where distances are best described in astronomical units rather than in Earth diameters. The planetary neighbourhood is still within the Sun's strong gravitational control, but it is far enough from Earth that direct intuition fails and must be replaced by geometry, orbital timing, and the travel time of signals. The most immediate fact is that planets are not arranged like beads on a line with fixed spacing. Each follows an orbit around the Sun, and those orbits are ellipses that are close to circles for many planets. The distance between two planets depends on where they are in their orbits at a given time. Sometimes they are on the same side of the Sun and closer together, sometimes they are on opposite sides and far apart. This changing geometry is part of scale, because it means there is no single number that describes the distance from Earth to a neighbour. Instead, there is a range. For each neighbour there is a closest approach and a farthest separation, both set by orbital radii and by orbital positions. Venus is the nearest planetary neighbour in terms of orbit. Its orbit lies inside Earth's. At its closest, Venus can come within a few tens of millions of kilometres. At its farthest, it is much farther away because the Sun sits between. These values can be expressed in astronomical units. Venus orbits at a little under 1 astronomical unit while Earth orbits at 1. The difference between their orbital radii gives a minimum possible separation when they align on the same side. The sum gives a maximum when they are opposite. Even in the closest case, the distance is large enough that a spacecraft takes months to travel. Using typical chemical propulsion trajectories and radio signals take minutes to cross. Mars is the next familiar neighbour, and its orbit lies outside Earth's. Like Venus, its distance from Earth changes with alignment. When Earth and Mars align on the same side of the Sun, in a favourable configuration, the distance can be relatively small by interplanetary standards, allowing shorter travel times for spacecraft. When they are on opposite sides, the distance increases greatly. These changes repeat with a rhythm set by the synodic period, the time between similar alignments as seen from Earth. This period arises because Earth and Mars orbit at different speeds. Earth's orbit is faster, so it periodically catches up. This provides a steady time framework for interplanetary geometry and for mission planning. The rhythm is not a human invention. It is a consequence of gravity and orbital radius. Mercury is closer to the Sun than Venus, and has a more eccentric orbit, meaning its distance from the Sun varies more. As a result, Mercury's distance from Earth varies widely, and its visibility is always constrained by its proximity to the Sun in the sky. The inner solar system is therefore not only large in distance, it is also a region where viewing angles matter. A planet can be nearby in distance, and yet hard to observe because it appears close to the Sun's glare. This is another lesson of scale. Space is not arranged for convenience. Observation depends on geometry. The Sun itself is the central reference. Its radius is about 700,000 kilometers. Compared with Earth's radius, it is more than 100 times larger. In volume, it is far larger still. Yet the Sun is distant from Earth by about 1 astronomical unit, 150 million kilometers. This means that even the Sun, which dominates the sky and drives climate, is separated by an enormous gap. Light takes a little over 8 minutes to travel from the Sun to Earth. That travel time is a direct physical measure. It can be tested by observing the delay between changes on the Sun and their effects on instruments in space and on Earth. In this planetary neighborhood, light travel time becomes a useful scale language because it converts distance into a familiar interval. Between the planets lies interplanetary space filled with the solar wind, a flow of charged particles from the Sun, and threaded by the Sun's magnetic field. The density of material is extremely low compared with air, yet it is not zero. The solar wind carries energy and momentum. It shapes planetary magnetospheres and contributes to phenomena such as auroras. It also sets a boundary of influence, but here it serves mainly to define the character of the region. The inner solar system is not a static emptiness. It is a structured medium shaped by the Sun with conditions that change as distance from the Sun increases. Distances in this region can be held in a consistent form by using the astronomical unit as a step size. Earth's orbit defines 1 unit. Venus orbits inside it, Mars outside it. The key point is that even within a few astronomical units, the scale is already beyond direct human experience. A spacecraft's travel time is governed not only by distance but by orbital mechanics. It must match speeds and trajectories. The most energy-efficient paths are curved following transfer orbits. This means travel time is often longer than a simple distance divided by speed. In the inner solar system, months are a common travel scale for robotic missions. This time scale reflects both the large distances and the constraints of orbital energy. The planetary neighborhood also introduces a shift in perspective about size versus distance. Planets are large compared with human scales, but tiny compared with the spaces between them. Earth is about 12,000 kilometers across. The distance to the Sun is about 150 million kilometers, more than 10,000 Earth diameters. The distance to Mars at favorable alignment can be tens of millions of kilometers, still thousands of Earth diameters. This ratio of object size to separation is a defining feature of the solar system. Planets are points separated by enormous gaps, and most of the volume is empty. The feeling of vastness comes more from these gaps than from the objects themselves. This region ends when the inner planetary orbits and their changing alignments have been accounted for as a coherent scale system. It establishes the astronomical unit, the idea of variable distances set by orbital geometry, and the use of light travel time as a practical measure of separation. It is still close enough that spacecraft have travelled through it repeatedly, yet it is already large enough that the mind must rely on measured numbers and on the steady logic of orbits rather than on ordinary spatial intuition. From the inner planetary neighborhood, the next region is the full scale of the solar system, moving outward through the orbits of the giant planets and into the broad domain where the Sun's gravity and radiation shape space far beyond the inner worlds. The solar system is not a tight cluster. It is a wide system where the outer planets are separated by distances that make the inner region seem compact. At this scale, the astronomical unit remains useful, but another measure becomes practical: the travel time of light across the system and the long orbital periods that mark how slowly distant worlds move. Jupiter is the first major step outward. Its orbit lies several astronomical units from the Sun far beyond Mars. Jupiter is the largest planet with a diameter more than 10 times that of Earth, and it carries a strong gravitational influence that shapes the solar system's architecture. Yet the most important scale feature here is distance. Jupiter's orbital radius is several times Earth's, so the distance from Earth to Jupiter ranges widely depending on alignment. Even at its closest, the gap is immense. Radio signals to spacecraft near Jupiter take tens of minutes to travel one way. That delay is operationally significant. Commands must be planned and executed with long feedback loops. This is how scale becomes tangible, not through imagining kilometers, but through the fact that even light needs a noticeable time to cross the distance. Beyond Jupiter lies Saturn, then Uranus, then Neptune. Each step outward increases distance and decreases the Sun's apparent brightness. The solar energy per unit area falls with the square of distance, so a world twice as far receives 1/4 of the sunlight. By the time the outer planets are reached, sunlight is weak and the environment is darker and colder. Yet the planets remain in orbit because gravity is still strong enough to bind them. Their orbital periods grow with distance. Jupiter takes about 12 years to orbit the Sun. Saturn takes about 30 years. Uranus takes about 80 years. Neptune takes about 160 years. These periods are a second kind of scale measure. They show that motion slows as distance increases. A year at Neptune is longer than a human lifetime. From an observer on Earth, Neptune's position against the background stars changes slowly, and its seasonal cycle, if defined by its long orbit and its axial tilt, unfolds over spans that exceed ordinary historical time. The outer solar system also includes many smaller bodies. Beyond Neptune is a region of icy objects that orbit in a band. These include dwarf planets and many smaller worlds. Their distances are often described in tens of astronomical units. The number itself is less important than the pattern the solar system extends far beyond the last major planet. The Sun's gravity binds objects on orbits that can be long and slow. Some of these objects have highly elliptical orbits that take them far out and then back in over long periods. Their presence shows that the solar system's mass distribution is not limited to the classical planets. A practical outer boundary of the solar system is sometimes described by the region where the Sun's direct influence carried by the solar wind gives way to the interstellar medium. The solar wind flows outward and forms a bubble in space. Inside the bubble, the solar wind dominates the local particle environment. At some distance, the solar wind slows as it meets interstellar material. This produces a termination shock where the wind transitions from supersonic to subsonic flow. Farther out, there is a boundary where the solar wind's influence is balanced by the surrounding interstellar environment. That boundary is called the heliopause. It is not a rigid shell. It can move and change shape with solar activity and with the conditions of the interstellar medium, but it provides a useful scale marker. It marks a region where the Sun's charged particle outflow no longer dominates. The heliopause lies far beyond the orbit of Neptune at a distance measured in more than 100 astronomical units. At this distance, light from the Sun is still bright enough to be measured, but it is much fainter than at Earth. The time for a radio signal from Earth to reach a spacecraft near this boundary is many hours. This is another shift from the inner system. In the inner system, minutes matter. In the outer system, hours matter. The delay becomes a central feature of operations and of any attempt to maintain contact. Beyond the heliopause, the Sun's gravity still extends, but the solar wind's direct influence is reduced. Gravity has no sharp edge. Its strength declines with the square of distance, but it remains non-zero. The question becomes not whether gravity exists, but whether the Sun's gravity dominates over the gravity of other stars and over the tidal field of the Milky Way. This leads to a larger, more diffuse region, sometimes described as a reservoir of long-period comets. This region would extend far beyond the heliopause, perhaps thousands to tens of thousands of astronomical units. The exact structure is uncertain because it is difficult to observe directly. What is known is that the solar system's gravitational influence can perturb and retain distant small bodies on very long orbits, and that the galaxy's gravity and passing stars can also perturb those orbits over long time. At this stage, the solar system's scale can be framed in multiple ways. In kilometers, the numbers become unwieldy. In astronomical units, they become manageable but still abstract. In light travel time, the scale becomes intuitive. Light from the Sun reaches Earth in a little over 8 minutes. Light reaches Jupiter in tens of minutes. Light reaches Neptune in several hours. Light reaches the heliopause in many hours. These intervals are the solar system written as time. They show that the solar system is not a small local neighbourhood. It is a vast space where even the fastest possible signal has a measurable delay. The Sun's influence is also expressed in temperature and in radiation. The outer solar system is cold not because it is close to a deep space boundary, but because sunlight is weak. This sets the physical conditions of outer worlds. Ices that cannot exist near Earth can remain stable. Atmospheres behave differently. Volatile substances can freeze and sublimate depending on seasonal cycles that last decades or centuries. These physical conditions are a consequence of distance. They are part of what scale means in a functional sense. This region ends when the solar system is seen as a complete structure, inner rocky planets in a compact zone, giant planets and icy bodies spread across a much wider zone, and a solar wind bubble that defines a boundary of particle influence far from the Sun. The solar system's size is therefore best understood as the span from Earth's orbit to the heliopause and beyond, expressed in astronomical units and in the hours it takes light to cross. The next step outward will leave the Sun's domain and enter the true separation between stars where even the nearest neighbours are far beyond the solar system's widest boundaries. From the full breadth of planetary orbits and the solar wind bubble, the next region is the edge of solar influence in a deeper sense, where the solar system is no longer defined by the solar wind or by the traditional map of planets, but by how far the Sun can hold objects against the background gravitational field of the Milky Way and against the perturbations of passing stars. This region is not a clear boundary that can be drawn with a single line. It is a gradual fading of dominance. The Sun's gravity weakens with distance while external influences remain present. The transition is therefore best understood as a change in which forces set the long-term fate of small bodies. Within the heliopause, the solar wind shapes the local plasma environment, but beyond it, the interstellar medium becomes the dominant charged particle background. Yet gravity continues outward with no abrupt stop. An object at a great distance from the Sun still feels the Sun's pull, but it also feels the gravitational field of the galaxy as a whole, and it can be influenced by the gravity of other stars that pass nearby over long time spans. These external influences are small at any given moment, but over millions of years they can change orbits. In the inner solar system, planetary perturbations dominate orbital changes. In the far outer solar system, the slow pull of the galaxy and rare stellar encounters become more important. A useful concept in describing the far boundary of a gravitational system is the Hill sphere, the region around a body, where its gravity dominates over the tidal field of a larger body. For the Sun, the larger body is not a single object but the galaxy. The Sun orbits the galactic centre and experiences a tidal field from the galaxy's mass distribution. The Sun also passes near other stars as it moves through the galactic disk. The Sun's effective Hill sphere with respect to the galaxy is vast compared with the planetary region, yet it is not infinite. Within that region, orbits around the Sun can remain bound over long spans. Beyond it, objects are more easily stripped away by galactic tides or by passing stars. The exact size depends on the local galactic environment and on how one defines stability over time, but the key point is that the solar system's gravitational reach extends far beyond the heliopause, fading gradually into the background of the Milky Way. This outer gravitational region is often discussed in connection with long-period comets, small icy bodies that appear in the inner solar system on highly elongated orbits. Their orbital periods can be thousands or tens of thousands of years. Their aphelia, the farthest points from the Sun, can lie at distances of many thousands of astronomical units. These bodies, when they exist, form a sparse cloud rather than a ring. The cloud is not directly observed as a whole because its members are faint and far apart. What is observed are the comets that are perturbed inward. Their presence implies a reservoir at great distance, where the Sun's gravity still binds material, yet where orbits are sensitive to small external nudges. Galactic tides provide one of those nudges. The Milky Way's gravity is stronger toward its centre and weaker farther out. Because the solar system is extended in space, different parts of it feel slightly different gravitational pulls from the galaxy. This difference is a tidal effect. Over long time, tides can change the orientations and eccentricities of distant orbits. A comet that spends most of its time far from the Sun can have its orbit slowly twisted, so that its perihelion, the closest point to the Sun, moves inward. When the perihelion becomes small enough, the comet enters the inner solar system and becomes visible. This process shows that at extreme distances the solar system is not isolated. The galaxy is always present as a weak but persistent influence. Passing stars provide another perturbation. The space between stars is vast, but stars move, and over millions of years close approaches occur. A close approach in this context is still a large distance by human standards, but it can be close enough to disturb distant small bodies. A passing star can slightly change a comet's orbit, either sending it inward or ejecting it entirely. Over the solar system's lifetime, many such encounters occur. Most are distant enough to have only small effects, but the cumulative influence contributes to the gradual loss and reshaping of the farthest bound reservoir. This again emphasizes that the edge of solar influence is not a wall. It is a region of slow exchange where some bodies remain bound and some are stripped away. The scale here can be expressed by comparing distances. The heliopause lies at a bit more than 100 astronomical units. The realm where long-period comet reservoirs may exist extends to thousands or tens of thousands of astronomical units. This is a jump of 2 orders of magnitude. In kilometers, it is a leap so large that the numbers lose ordinary meaning. In light travel time, it becomes clearer. Light takes hours to reach the heliopause. It takes days to reach distances of thousands of astronomical units. Even so, these light travel times remain tiny compared with the next region beyond the solar system, which is the distance to the nearest stars. The farthest gravitational reach of the Sun, as described here, approaches but does not exceed that interstellar gap. It is the outer skin of the solar system before the true domain of star-to-star separation begins. Another way to sense this region is through orbital periods. A body at 100 astronomical units has an orbital period of about 1,000 years. A body at 10,000 astronomical units has an orbital period of about 1,000,000 years. These periods show how slowly motion unfolds at the edge. A complete orbit can take longer than recorded human history, then longer than the time since early human ancestors, then longer than the evolution of many species. The solar system's outermost bound region is therefore a place where movement is so slow that a single body can remain on a similar trajectory across major changes in the galaxy, yet still be vulnerable to rare perturbations. This region also reveals how the solar system's scale depends on definition. If the solar system is defined by the planets, it ends at Neptune. If it is defined by the solar wind bubble, it ends at the heliopause. If it is defined by gravitational binding, it reaches much farther into a diffuse cloud where the sun's pull still dominates locally, but competes with the galaxy. Each definition is physically grounded. None is purely semantic. They simply focus on different kinds of influence. By finishing this region, the solar system is now complete not only as a set of planets and a solar wind bubble, but as a gravitational territory with a fading edge. The next step outward will leave this territory and enter the true distance between stars, where the unit of measurement shifts again, and the gaps become larger than the entire scale built so far. From the fading edge of solar influence, the next region is the space between stars, beginning with the nearest stellar neighbours. This is the first point where the solar system, even in its widest gravitational sense, becomes a small island in a much larger ocean. The defining feature here is separation. Stars are not arranged in tight clusters across most of the Milky Way's disk. They are separated by distances that are enormous compared with planetary scales. To describe these distances, a new unit becomes useful: the light year, the distance light travels in 1 year in vacuum. It is not a time unit here, but a distance unit anchored to a universal speed. The nearest star system to the Sun is a small group of stars called Alpha Centauri. It includes at least 3 stars, 2 Sun-like stars in a close pair, and a smaller red dwarf farther out. The distance to this system is a little more than 4 light years. That number can be translated into the solar system scale. The heliopause is a little more than 100 astronomical units. A light year is about 63,000 astronomical units. This means that the nearest star is tens of thousands of times farther away than the Sun's solar wind boundary, and still thousands of times farther than the region where distant comets may orbit. The gap is so wide that the entire solar system, even with its farthest bound cloud, occupies only a tiny fraction of the distance to the nearest star. Light travel time makes the separation tangible. A radio message sent from Earth to a probe at the heliopause takes hours. A message sent to Alpha Centauri takes more than 4 years. A reply takes another 4. This means that even the fastest possible conversation across that gap unfolds over nearly a decade. Any physical travel is far harder. Even the fastest spacecraft launched from Earth so far would take many thousands of years to reach the nearest star. This is not a matter of engineering preference. It is a direct consequence of the enormous distance compared with attainable speeds. The nearest stars beyond Alpha Centauri include other red dwarfs such as Barnard's star and others within a few light years. Many of the closest stars are red dwarfs because they are the most common kind of star in the galaxy. They are small, cool, and faint compared with the Sun, which makes them harder to see with the naked eye even when they are nearby. This is another lesson of scale proximity does not guarantee brightness. The brightness of a star depends on both distance and intrinsic luminosity. A nearby faint star can be less visible than a distant bright star. As a result, the night sky's bright points do not map directly to the nearest stars. The nearest stars are often modest and easily overlooked without careful measurement. The distances between stars can be pictured by comparing to the size of stellar systems. A star's radius may be about 1 million kilometers for a Sun-like star. Its planetary system extends to tens of astronomical units for the main planets, and perhaps to hundreds for the solar wind boundary. Even if a planetary system extends to thousands of astronomical units in a comet reservoir, it is still tiny compared with several light years. The gap is mostly empty. The interstellar medium contains gas and dust, but its density is extremely low. In many regions near the Sun, there may be only a few atoms per cubic centimetre. Dust grains are sparse, yet over light-year distances, even this thin material accumulates into measurable effects. It can absorb and scatter light, especially at shorter wavelengths. It can also form clouds that become the raw material for future stars. The interstellar medium is therefore not nothing. It is a very thin substance spread across an immense volume. The local region of the Milky Way around the Sun is sometimes described as a neighbourhood within a few tens of light years that contains many stars. In this neighbourhood, typical separations between stars are a few light years. This means that if one imagines a sphere centred on the Sun with a radius of 10 light years, that sphere contains a modest number of stars. If the radius is increased to 50 light years, the number increases greatly because volume grows with the cube of radius. Yet even in such a volume, the average separation remains large compared with planetary scales. Space remains mostly empty, and stars occupy almost none of the volume. The scene is defined by isolated points with vast gaps between them. Distances to stars are measured with methods that become more reliable as instruments improve. The simplest method for nearby stars is parallax the apparent shift in a star's position against more distant background stars as Earth orbits the Sun. By measuring the shift over 6 months, astronomers can infer distance through geometry. Parallax angles are small even for the nearest stars. This smallness itself is a sign of scale. It means that Earth's orbit 1 astronomical unit is tiny compared with the distances involved. Only with precise instruments can the shift be measured well. Once distances are known, the light year becomes a stable unit for mapping neighbourhood structure. The step outward here also introduces a change in the nature of travel and influence. In the solar system, gravity from the Sun dominates and orbits are coherent within one system. Between stars, the Sun's gravity becomes negligible. A spacecraft leaving the solar system enters a region where the gravitational field is the sum of many distant stars and the galaxy as a whole. For long stretches it would move almost inertially with only slight gravitational deflection. There are no large bodies for navigation by close encounter. The environment is quiet, cold and sparse. From the perspective of scale, the important point is that the first interstellar distance is already vast enough to dwarf all previous steps. If Earth is the unit, then the Moon is a large step, the Sun is a far step, the heliopause is a farther step, and the gravitational edge is farther still. Yet the nearest star multiplies the distance again by a factor that is hard to hold without a new unit. The light year provides that unit and anchors it to the constant speed of light which can be tested locally. This allows the mind to translate the abstract into a consistent ladder. The solar system is measured in astronomical units, while star separation is measured in light years. This region ends with the nearest stellar neighbours defined by their distances and by the emptiness between systems. The next step outward will expand from the nearest few light years to the broader local stellar neighbourhood within the Milky Way, where the number of stars grows and the structure of the galaxy begins to appear as a large-shaped system rather than a scattering of isolated points. From the nearest few stars, the next region is the broader local stellar neighbourhood, the space within tens to hundreds of light years, where the Milky Way's star field begins to reveal its density, variety and structure. This region is still only a tiny part of the galaxy, but it is large enough that patterns emerge. Stars are no longer counted one by one as rare neighbours. They become a population with distributions in mass brightness, motion and age. The real size of the universe cannot be approached without first seeing how quickly a local volume fills with stars when the radius expands, and without understanding that even this filled volume remains minuscule compared with the full galaxy. The Sun sits in a region of the Milky Way's disk where stars are relatively spread out. The typical separation of nearby stars remains on the order of a few light years, but the local volume contains a mixture of star types. Most are low-mass red dwarfs, faint and long-lived. There are fewer Sun-like stars and fewer still massive bright stars because massive stars are rare and short-lived. This means that the local neighbourhood, when mapped by number, is dominated by faint stars. When mapped by light, it can appear dominated by a smaller number of brighter stars that can be seen from farther away. This difference matters for perception. The night sky's brightest stars are not always the closest. Some are luminous enough to be visible despite being many tens or hundreds of light years away. As the radius of the neighborhood increases, the number of stars grows quickly, because volume grows with the cube of radius. A sphere of space with a radius of 10 light years contains only a limited number of stars. A sphere with a radius of 100 light years contains a much larger number, because its volume is 1,000 times greater. Yet even in 100 light years, the galaxy is still sparse enough that most of space is empty. The stars occupy extremely small volumes compared with the void between them. This means that when imagining the neighborhood, the correct picture is not a fog of stars packed together, but a wide volume dotted with points. The local neighborhood also includes moving stars. Stars orbit the galactic center, and they also have random motions relative to the average rotation of the disk. These motions are measured as proper motion across the sky and radial velocity along the line of sight. Over human lifetimes, the motion is small for most stars, but it can be measured for nearby ones. Over thousands of years, constellations change shape. Over millions of years, the local neighborhood is rearranged completely with different stars passing near the sun and others moving away. This movement is a scale signal because it introduces long-term change without dramatic events. The sky is not a fixed dome, it is a dynamic map of objects in motion through a vast region. Within the local neighborhood, the interstellar medium is not uniform. There are regions of denser gas and dust and regions of lower density. The Sun is believed to be moving through a relatively low-density region, often called the local bubble, a cavity in the interstellar medium that may have been carved by past supernovae. The exact shape and origin are studied through observations of gas absorption and emission. The key scale point is that structures in the interstellar medium can span tens or hundreds of light years. These structures are large compared with the distances between stars, and they influence star formation by providing the raw material. When gas becomes dense enough, it can collapse under gravity and form new stars. The presence of such clouds in the broader neighborhood shows that even within a few hundred light years, the galaxy contains large-scale features beyond individual stars. Stellar groups and clusters provide another aspect of neighborhood structure. Some stars form in clusters where many stars are born together from the same molecular cloud. Over time, clusters can disperse as stars drift away. Open clusters are examples of relatively young groupings. They can be found within the disk and can be observed as concentrations of stars in the sky. Their sizes can be a few light years across, and their ages can range from millions to billions of years. The existence of clusters shows that stars are not always isolated in their formation. Yet the dispersion of clusters over time shows that the galaxy's gravitational environment and stellar motions slowly mix the population. The local neighborhood also contains remnants of dead stars. White dwarfs are the cooling cores left by stars like the Sun. Neutron stars are the remnants of more massive stars that explode as supernovae. Black holes can form from the collapse of very massive stars. These objects are small in size but important in understanding scale because they show that the region's mass is not all visible light. Many stars are faint. Some remnants are nearly invisible except through their gravitational influence or their radiation in specific bands. This means that the local neighborhood's true inventory includes many objects that are not obvious to the eye. The scale of the neighborhood is therefore better understood through surveys and instruments than through naked eye impressions. Distances within this region continue to be measured through parallax for nearby stars and through other methods such as spectroscopic estimation for more distant ones, where parallax becomes small and harder to measure. Modern measurements allow precise mapping of the local stellar distribution. This mapping reveals that the Sun is not near any special boundary. It is one star among many in a rotating disk. The local region has a certain stellar density, and that density can be measured as stars per cubic parsec, where a parsec is another distance unit used in astronomy. A parsec is defined by parallax geometry, the distance at which one astronomical unit subtends an angle of 1 arcsecond. A parsec is a little more than 3 light years. This unit becomes useful when describing densities and galactic structures because it is tied to a measurement method and scales conveniently for local distances. Even at 100 light years, the Milky Way is not yet seen as an object with a clear shape. The local region is a small patch. The Milky Way's full disk is many tens of thousands of light years across. This means that the local neighbourhood is like a small region on a large plane. The stars visible within a few hundred light years provide only local information, yet they are enough to reveal that the galaxy is a population system with motion, with star formation regions, with remnants and with large interstellar structures. The sense of scale here is that of accumulation. Each additional shell of distance encloses a large new volume, and therefore many more stars, yet the separations remain large and emptiness dominates. This is the character of the galaxy's disk near the Sun, a sparse distribution of stars embedded in a thin medium with large gas structures and moving stellar populations. The region ends when the local neighbourhood is understood as a statistical population, rather than a handful of named stars. The next step outward will turn from local population to the Milky Way itself, as a structure where the galaxy's overall size, thickness and spiral form become the focus. From the local neighbourhood of tens to hundreds of light years, the next region is the Milky Way as a whole, the galaxy that contains the Sun and the majority of the stars visible in the night sky. The Milky Way is a single gravitationally bound system, made of stars, gas, dust, dark matter, and a central massive black hole. Its size is so large that it cannot be grasped by looking at nearby stars alone. It is inferred through mapping motion and the distribution of matter across long distances. This region establishes the scale of one galaxy before stepping outward to other galaxies. The Milky Way is a disk galaxy with spiral structure. The disk contains most of the visible stars, gas and dust. The disk is thin compared with its width. Its thickness in the region of the Sun is on the order of a few thousand light years for the thin disk component, with a thicker component extending farther above and below the plane. The diameter of the stellar disk is on the order of 100,000 light years, though the exact boundary depends on how one defines the edge of the stellar distribution and how far faint stars extend. This means that the galaxy's width is vastly larger than the 100 light-year neighbourhood described earlier. The local region is less than 1% of the galaxy's diameter. Even the nearest stars occupy a tiny pocket within a structure that spans 100,000 light years. The Milky Way's disk is not a uniform sheet. It contains spiral arms regions where gas density and star formation are higher. Spiral arms are not fixed material arms in the way a rigid wheel has spokes. They are patterns, density waves or self-organized structures where gas is compressed and star formation occurs more frequently. As stars orbit the galactic center, they move in and out of these patterns. The arms are traced by young bright stars, by glowing gas clouds, and by dust lanes that block light. From inside the disk, these structures appear as bright bands and dark rifts in the Milky Way's glow. The Milky Way seen in the sky is the view along the plane of the disk where the line of sight passes through large numbers of stars and through dust. Dust is important for understanding the galaxy's structure because it obscures visible light. Dust grains, though sparse, can block and redden starlight over long distances. This means that the Milky Way's far side is difficult to see in visible light from Earth's position. Astronomers therefore use longer wavelengths such as infrared and radio, which pass through dust more easily. Radio observations of neutral hydrogen, for example, reveal large-scale structures and the distribution of gas across the disk. By combining observations across wavelengths, a fuller map of the galaxy emerges. The Milky Way also contains a central bulge, a dense region of stars around the galactic center. The bulge extends several thousand light years and contains older stars on more varied orbits than those in the disk. At the very centre lies a supermassive black hole with a mass of millions of suns. Its presence is inferred from the motions of stars orbiting extremely close to the centre. These stars move rapidly, tracing orbits that can be measured over years and decades. Their speeds and orbital shapes indicate a compact central mass. The black hole itself is not a dominant fraction of the galaxy's mass, but it is a central anchor and a key feature in understanding the galaxy's dynamics. Surrounding the disk and bulge is a halo. The halo contains old stars' globular clusters and a much larger component of dark matter. Dark matter does not emit light and is detected through its gravitational influence. The rotation curve of the Milky Way, the way orbital speed varies with distance from the centre, does not match what would be expected if only visible matter were present. Instead, stars and gas at large radii orbit faster than visible matter alone would allow, indicating an extended halo of mass. This halo extends far beyond the visible disk, possibly hundreds of thousands of light years. This adds another layer of scale. The galaxy's gravitational reach is larger than its luminous boundaries. The luminous disk might be 100,000 light-years across, but the mass distribution that binds satellites and influences motion extends farther. The galaxy's overall mass and structure are also inferred by observing the motions of satellite galaxies and globular clusters. The Milky Way has smaller companion galaxies that orbit it, including dwarf galaxies. Their orbits are shaped by the Milky Way's gravitational field. By measuring their velocities and positions, astronomers can estimate the mass of the Milky Way within their orbits. This provides constraints on the halo's size and on the distribution of mass. From within the galaxy, mapping its size involves distance measurements to star clusters, variable stars and other standard candles objects, whose intrinsic brightness can be inferred from measurable properties. By comparing intrinsic brightness to observed brightness, distances can be estimated. This allows the three-dimensional distribution of stars to be mapped, at least where dust does not fully obscure. The Sun's distance from the galactic centre is on the order of tens of thousands of light years, placing it in the disk not near the centre and not near the edge. At this position, the Sun orbits the galactic centre in a period of hundreds of millions of years. This orbital period is another scale marker. A single orbit around the galactic centre takes far longer than the time humans have had recorded history. It is a slow cycle that frames the Sun's motion through spiral patterns and through regions of different interstellar conditions. The Milky Way's star count is enormous, on the order of hundreds of billions of stars, though the exact number depends on the faint end of the distribution and on how the galaxy's structure is defined. The exact count is less important than the contrast it reveals. The local neighbourhood contains a few dozen stars within 10 light-years, then a few thousand within 100 light-years, and then the galaxy as a whole contains hundreds of billions across 100,000 light-years. This escalation shows how scale grows when moving from local to galactic. The Milky Way is therefore both a shape and a volume. It is a thin disk with spiral patterns, a central bulge, and an extended halo of old stars and dark matter. It contains gas clouds where stars form and dust that hides large regions from view. It is a single system bound by gravity, rotating as a whole, with internal motions and long-term evolution, driven by star formation, stellar death, and interactions with satellites. This region ends with the Milky Way established as one galaxy, a structure tens of thousands of light-years in radius, far larger than the local neighbourhood, yet still one object among many in the universe. The next step inward within this outer to inner path will not move deeper into the Milky Way's centre yet. Instead, it will orient the observer's position within this structure, clarifying where the Sun sits relative to the disk arms and centre, before stepping outward beyond the galaxy to neighbouring galaxies. With the Milky Way established as a disk bulge and halo system of great size, The next region narrows to orientation inside that structure locating the Sun and Earth within the galaxy's geometry. This is still a large-scale view, but it is more specific. It treats the observer not as an outside viewer looking at a whole galaxy in one frame, but as a point embedded within the disk moving along with the galaxy's rotation and seeing the Milky Way's features from the inside. From this position, many of the galaxy's properties must be inferred indirectly, because lines of sight pass through dust-crowded starfields and long distances that blend together. The Sun sits within the Milky Way's disk, not in the central bulge and not at the edge. Its location is commonly described by its distance from the galactic center and its height above or below the midplane of the disk. The distance to the center is on the order of tens of thousands of light years. This places the Sun well inside the disk's broad radius, in a region where there are many stars but not in the very dense central zones, where star crowding and gravitational forces are strongest. The Sun's height relative to the galactic plane is small compared with the disk's thickness, meaning it remains close to the midplane, where most of the galaxy's gas and dust also concentrate. This matters because the plane is where the Milky Way appears brightest in the sky, and it is also where dust obscuration is strongest. From Earth, the Milky Way is seen as a luminous band because the line of sight through the plane of the disk passes through a long column of stars. Looking along the plane, the observer looks through thousands of light years of the disk, sampling many more stars than when looking out of the plane. Looking perpendicular to the plane, the line of sight exits the dense disk more quickly, so the sky contains fewer stars and less dust, and more distant galaxies become visible. This directional difference is a direct consequence of the Sun's embedded position. The Milky Way's band is not a separate object laid across the sky. It is the view through the galaxy's own disk from the inside. The galactic center lies in a specific direction in the sky, and it can be identified by mapping star density gas emission and the motions of stars and gas in that region. Invisible light dust blocks much of the direct view toward the center. In infrared and radio wavelengths, the center becomes more accessible, revealing dense star populations and bright emission from gas. The central region includes the supermassive black hole and a surrounding environment of strong gravity, high stellar density, and complex gas dynamics. The Sun's position far from the center means that the central environment is not part of everyday local conditions, yet it shapes the overall gravitational potential that defines the Sun's orbit. The Sun moves around the galactic center as part of the disk's general rotation. This motion is not a simple circular path in an unchanging field, but it is close enough to circular for a broad description. The orbital speed is on the order of a few hundred kilometers per second, and the orbital period is on the order of a few 100 million years. This long period is a scale marker that sits between stellar lifetimes and planetary years. It frames how the solar system's environment changes over geological time. Over one orbit, the Sun passes through different galactic longitudes and can move relative to spiral arm patterns. The motion also means that the local neighborhood of stars is not fixed. Stars drift relative to one another, and over millions of years the set of near neighbors changes. The Sun's position is often discussed relative to spiral arms. Spiral arms are regions of higher gas density and star formation, traced by young luminous stars and by glowing gas. Because the Sun is not extremely young, and because it is not in a major star-forming region, its exact placement relative to strong arm segments is described as being in an interarm region, or near a smaller feature between larger arms. The key physical point is that the disk is structured and not uniform, and the Sun's environment is not identical to the environment closer to major star-forming ridges. Gas density and dust content can vary with location in the disk, affecting the frequency of nearby massive stars and the local radiation background over long spans. From the Sun's position, much of the Milky Way structure must be reconstructed through distance measurements and velocity mapping. gas clouds emit radio waves at characteristic wavelengths, and these emissions can be measured across the sky. Because gas rotates around the galactic centre, its velocity relative to the observer produces Doppler shifts, changes in observed frequency that indicate motion toward or away. By combining measured velocities with models of galactic rotation, astronomers infer where gas lies along the line of sight, though there can be ambiguity in certain directions. Stars also provide structure signals. Star counts, stellar colours, and the distribution of certain types of variable stars reveal the disk's thickness, the bulge's extent, and the presence of streams and remnants of past mergers. The Sun's embedded position also explains why the Milky Way's full shape is hard to see directly. A person inside a forest cannot see the forest's outline by looking at nearby trunks. The person sees local density and partial corridors, but the overall boundary is obscured by the environment itself. In the galaxy, dust plays the role of obscuring material, especially toward the inner disk and the centre. In addition, distance, uncertainty, and crowding complicate the view. Many stars overlap along a line of sight, and their apparent brightness does not directly reveal distance without additional information. This is why the galaxy's size and spiral structure are mapped through large surveys and through methods that connect observable properties to distance. The Sun's location within the disk also connects to the galaxy's vertical structure. The disk has a mid-plane where gas and young stars concentrate. Over time, stars can be scattered into thicker distributions by gravitational interactions, including encounters with giant molecular clouds and the influence of spiral patterns. Older stars tend to have larger vertical motions and can be found farther from the plane than younger stars. The Sun's present vertical position is modest, and it oscillates up and down through the plane over time. This oscillation is a gentle motion within the galaxy's gravitational field. It is a further example of how the solar system is not simply travelling in a flat circle, but moves in 3 dimensions, though the vertical range is small compared with the galaxy's full size. The observer's position affects how distances are interpreted. Looking toward the galactic centre, distances are compressed in angular space, because many features lie at different distances along similar directions. Looking away from the centre, the line of sight can exit the disk more quickly, and the star density drops. The brightness of the Milky Way band varies around the sky, because some directions pass through denser regions or longer path lengths in the disk. The dark rifts seen in the Milky Way are caused by dust clouds that block background starlight, making gaps and lanes. These dark structures are local to intermediate distances, not empty holes in the galaxy. They demonstrate that the view is shaped by intervening material. The Sun's position within the galaxy also sets the background against which the next scale steps will be understood. When stepping outward to nearby galaxies, it matters that the Milky Way is one disk among many, and that from within it external galaxies are seen through the thinner directions where dust and star crowding are less intense. This is why the night sky's windows to the distant universe are strongest away from the galactic plane. The local orientation therefore shapes what can be seen of the universe beyond the Milky Way. This region also clarifies a mental contrast between local and galactic scales. Locally, within a few light years, stars are separated by large gaps and appear as isolated points. At galactic scale, the same stars become part of a disk, with coherent rotation density gradients and structured patterns. The Sun's position is the bridge between these scales. It is a local star with planets and a small gravitational domain, yet it is also one moving component within a rotating disk tens of thousands of light-years across. The local perspective often hides this membership because the nearest environment looks sparse and empty. The galactic perspective restores it by showing that sparsity is the normal state of a disk galaxy, and that the appearance of a glowing Milky Way band comes from long lines of sight through the disk, not from close packing of stars. By completing this orientation, the Milky Way is no longer only an external description of a galaxy's shape. It becomes a lived coordinate system in which Earth and the Sun have an address within the disk far from the centre, near the plane moving along with the galaxy's rotation. The next step outward will leave the internal viewpoint and move beyond the Milky Way to the nearest external galaxies, where even the space between galaxies becomes the defining scale. With the observer located inside the Milky Way's disk, the next region moves outward beyond the galaxy's boundary, to the nearest external galaxies. This is the first step where the Milky Way becomes one object among others, and where intergalactic space becomes the dominant feature between large systems. The scale shift here is substantial. The distance to the nearest major galaxies is hundreds of thousands to millions of light-years, far larger than the Milky Way's own thickness, and comparable to or larger than its diameter. These distances make the light-year essential, and they begin to introduce the million light-year scale as a common measure. The nearest large galaxy to the Milky Way is the Andromeda Galaxy, a spiral galaxy, similar in broad type to the Milky Way, though different in specific structure and mass distribution. Its distance is on the order of a few million light-years. This means that light leaving Andromeda travels for millions of years before reaching the solar system. The galaxy seen in the night sky is therefore not Andromeda, as it is now in any absolute sense, but a record of its state in the distant past. Even so, because millions of years are short compared with the full lifetime of galaxies, Andromeda's overall appearance remains broadly representative of its current structure. The key scale point is that a single neighbouring galaxy lies at a distance that dwarfs the entire Milky Way's internal star-to-star separations. Andromeda is visible to the unaided eye under dark skies as a faint smudge, because it is large and relatively nearby by extragalactic standards. Its faintness, despite its enormous size, demonstrates the effect of distance on brightness. A galaxy can contain hundreds of billions of stars, yet at a distance of millions of light-years it can appear as a subtle glow. This reflects inverse square spreading of light, and the fact that the light from many stars is spread across an extended area on the sky. The galaxy's total light is large, but it is diluted by distance and by its angular size. Another notable nearby galaxy is the Triangulum Galaxy, smaller than Andromeda, and also a spiral galaxy. It lies at a distance of a few million light-years as well, part of the same local gravitational environment. Beyond these there are smaller galaxies, many of them dwarf galaxies that orbit the Milky Way and Andromeda. Some dwarf galaxies lie much closer at distances of tens or hundreds of thousands of light-years, making them satellites within the Milky Way's extended halo. Examples include the Magellanic Clouds visible from the southern hemisphere as bright patches of sky. They are not clouds in the atmospheric sense. They are dwarf galaxies with their own star populations, gas and internal structure. Their visibility again shows that a galaxy can be close enough to appear as a distinct object in the sky, yet still be far beyond any travel scale. Light from the Magellanic Clouds takes on the order of hundreds of thousands of years to arrive. The existence of satellites demonstrates that the Milky Way's gravitational influence extends far beyond its luminous disk. Dwarf galaxies can orbit within the halo, moving in paths shaped by dark matter and by the Milky Way's mass distribution. They can also interact with the Milky Way with tidal forces pulling out streams of stars and gas. These streams are observed as faint structures in the halo. This shows that the boundary of a galaxy is not a clean edge. It is a region where gravity and interaction extend beyond the bright disk. Between the Milky Way and Andromeda, and between any galaxies lies intergalactic space. Intergalactic space contains gas often extremely thin, and it contains dark matter that forms part of the large-scale structure of the universe. It is not empty in an absolute sense, but it is far emptier than interstellar space within a galaxy. The density of baryonic matter, meaning ordinary matter, made of protons and neutrons is low, and much of it is ionized. Yet over millions of light years, this material forms a connected web feeding galaxies through slow flows and carrying the imprint of cosmic structure. For the scale ladder, the key point is that the vast distances between galaxies are dominated by near vacuum and by faint diffuse matter, not by intervening objects. The travel time of light across intergalactic distances introduces a new sense of delay. A radio signal sent from Earth to the Magellanic Clouds would take hundreds of thousands of years. A signal to Andromeda would take millions of years. This makes meaningful exchange impossible on any human timescale and emphasizes that galaxies are separate islands with their own internal evolution. The universe at this scale is not a tight community. It is a scattered field where interaction is governed by gravity over long spans and where information exchange is limited by vast light travel times. The Milky Way and Andromeda are not stationary relative to each other. Their mutual gravity draws them together, and their relative motion can be measured through Doppler shifts and proper motion studies. Over billions of years, they're expected to interact and eventually merge. This is another example of scale-driven slowness. The galaxies are moving, but the timescale for collision is measured in billions of years. For a human observer, the change is imperceptible. Yet in the cosmic framework, mergers are a normal part of galaxy evolution, shaping the growth of large galaxies over time. Distances to nearby galaxies are measured using a distance ladder, a set of methods that overlap in range. For relatively nearby galaxies, certain variable stars with known relationships between their pulsation periods and intrinsic brightness can be used. By observing their periods and apparent brightness, distances are inferred. For larger distances, other standard candles and methods are used. The accuracy of these methods has improved greatly with modern instruments, allowing more precise mapping of the local extragalactic environment. Again, the measurement method is less important here than the scale result. Nearby galaxies begin at hundreds of thousands of light years and extend quickly into millions. This region also shows that galaxies have sizes comparable to their separations in some cases. The Milky Way's luminous diameter is on the order of 100,000 light-years. The distance to some satellite galaxies is on the order of the same magnitude. This means that a galaxy's sphere of influence, including its halo and satellites, is a structure comparable to its separation from other major galaxies. The local environment is therefore a set of overlapping gravitational territories rather than isolated disks. By completing this region, the Milky Way has been placed among its nearest neighbours, with Andromeda and other galaxies as reference points. The universe has moved from the scale of stars within one galaxy to the scale of multiple galaxies separated by millions of light years. The next step outward will gather these nearby galaxies into a single bound system, the local group where gravity binds a small collection of galaxies into a coherent structure within the larger expanding universe. From individual neighbouring galaxies, the next region is the local group, the small collection of galaxies bound together by gravity that includes the Milky Way, Andromeda, and several dozen smaller galaxies. This region is defined not only by distance but by shared motion. The galaxies in the local group are close enough that their mutual gravity overcomes the general expansion of the universe within this volume. They orbit a common centre of mass in complex paths, and over long spans they interact, merge and exchange matter through tidal forces. The scale of the local group is measured in millions of light years, and it forms the first clearly defined extragalactic structure that the Milky Way belongs to. The local group spans a region a few million light-years across. The Milky Way and Andromeda are the two dominant members by mass, with Andromeda likely the more massive of the two, in many estimates, though the exact comparison depends on how their dark matter halos are measured. Triangulum is another significant spiral galaxy member smaller than the other two. Around these major galaxies are numerous dwarf galaxies. Some are satellites of the Milky Way, some are satellites of Andromeda, and some are more isolated within the group. The dwarfs vary in composition. Some contain gas and form stars. Others are gas-poor and contain mostly older stars. Their variety reflects both their formation histories and the stripping effects of larger neighbours. The local group is not a dense cluster. The separations between its member galaxies are large, often hundreds of thousands to millions of light-years. Most of the volume is intergalactic space containing thin gas and dark matter. Yet gravity binds the group because the total mass dominated by dark matter, halos of the major galaxies, creates a gravitational potential deep enough that the member galaxies do not simply follow the Hubble, flow the general recession of galaxies due to cosmic expansion. Inside the group, random and orbital motions dominate over expansion. This is why the Milky Way and Andromeda can be moving toward each other even though the universe expands on larger scales. The concept of being bound becomes clearer at this scale. A bound system is one in which objects have total energy that keeps them together. In practice, this means their relative velocities are not high enough to escape the gravitational pull of the system's mass. For the local group, the evidence for binding includes the observed velocities of its galaxies and the fact that the group has remained coherent over long cosmic time. The group's mass cannot be explained by visible stars and gas alone. The motions imply substantial dark matter. This dark matter is not seen directly, but its gravitational influence is inferred from galaxy dynamics. The local group structure is not symmetric. The Milky Way and Andromeda form a pair that dominates the group's dynamics. Their dark matter halos may overlap, or at least interact gravitationally across intergalactic space. The dwarfs around each major galaxy are distributed in complex patterns, including streams of stars torn from disrupted satellites. These streams show that the group is not static. It is a place where small galaxies can be gradually pulled apart by tidal forces as they orbit larger hosts. Over time, these processes contribute to the growth of the major galaxies and to the build-up of their halos. The local group also includes a diffuse medium. Gas exists between galaxies, though its density is very low. Some of this gas is ionized and difficult to detect. Yet observations in ultraviolet and X-ray bands and studies of absorption lines in the spectra of background sources indicate that gas in and around the group exists. This gas can act as a reservoir that feeds galaxies slowly, or as material heated by past interactions and energetic events. For scale, the important point is that even within a bound group, much of the ordinary matter is not in bright stars. It can be in thin, hot, or warm gas spread across the volume. The scale of the local group can be expressed by comparison to earlier steps. The Milky Way's luminous disk is on the order of 100,000 light-years across. The local group is several million light-years across, tens of times larger. The distance between the Milky Way and Andromeda is on the order of a few million light-years, comparable to the group's overall size. This means that the group is not a compact ball of many large galaxies. It is a sparse association dominated by two major galaxies separated by a large gap with smaller galaxies scattered around. The local group's timescales are also large. Orbital times for dwarf galaxies around the Milky Way can be billions of years. The eventual interaction between the Milky Way and Andromeda is expected on a scale of billions of years. These times are long compared with human history, and even compared with many evolutionary timescales on Earth. Yet they are not unusual for galaxy dynamics. The size of the group and the velocities involved naturally lead to such long times. Gravity operates steadily, and the system evolves through slow motion punctuated by mergers. Distances within the local group are measured with methods such as variable stars and other standard candles. These measurements allow astronomers to build a three-dimensional map of group membership. Membership is also assessed by velocity. A galaxy that lies within the same region of space and has a velocity consistent with being gravitationally influenced by the group is considered a member. Some galaxies near the group's edge may be borderline cases influenced partly by the group and partly by larger scale structures. The local group does not exist in isolation. It is part of a larger collection of galaxy groups and clusters called the local sheet or local filament, depending on the scale of description. Nearby groups include the group around the galaxy M81 and other associations. These groups are outside the local group but close enough in cosmic terms to be part of the same general region of the universe. The local group's boundary is therefore not a sharp border. It is a region where gravitational influence transitions to the broader expansion and to the influence of other structures. Yet the group remains a meaningful unit because its members share a bound relationship. In terms of the ladder of size from Earth to the farthest light, the local group is an important milestone. It is the first level where the Milky Way is understood as part of an external system, not just as a single galaxy among distant others. It shows that galaxies gather into small bound families. It also shows that the step from one galaxy to a group is not only a step in size, but a step in dynamical behavior. Within the group, gravity dominates over expansion. Beyond it, expansion becomes more visible. By finishing this region, the Milky Way and its nearest neighbours are consolidated into one bound structure measured in millions of light years. The next step outward will move to larger bound structures, galaxy clusters, where hundreds or thousands of galaxies occupy a region tens of millions of light years across, and where the scale of space between galaxies and the role of hot intergalactic gas become even more prominent. From the local group as a small bound family, the next region expands to galaxy clusters, much larger bound structures containing hundreds to thousands of galaxies. Clusters are among the largest gravitationally bound objects in the universe. They mark a scale where galaxies are no longer isolated islands separated by immense voids, but members of dense environments where interactions merges and the influence of hot gas become common. The scale of a cluster is measured in millions to tens of millions of light years, and its mass is dominated not by stars but by dark matter and by vast reservoirs of extremely hot gas. A galaxy cluster forms where matter is gathered in the cosmic web. Dark matter collapses under gravity to form deep potential wells. Ordinary matter, including gas, falls into these wells. As gas falls in, it is heated by compression and by shocks to very high temperatures. This hot gas fills much of the space between galaxies in the cluster. It emits X-rays, revealing the cluster's presence, even when its galaxies are not easily counted. The galaxies themselves move within the cluster's gravitational potential, typically at speeds of hundreds to more than 1,000 kilometers per second. These high speeds reflect the cluster's mass. They also indicate that close encounters between galaxies can be frequent, though the high speeds can make long mergers less common than in smaller groups depending on the encounter geometry. Clusters are identified in several ways. One is by counting galaxies in a region and finding a concentration above the background. Another is by detecting X-rays from hot intracluster gas. A third is by gravitational lensing, where the cluster's mass bends light from more distant galaxies, distorting their apparent shapes. Lensing provides a way to map mass, including dark matter, without relying on emitted light. These methods together reveal that clusters contain far more mass than is visible in their stars. The discrepancy is not small. The visible stars account for only a minor fraction. Hot gas contains more ordinary matter than stars in many clusters, and dark matter contains the largest share of mass. The nearest rich galaxy clusters are not in the local group, but they are part of the broader region of the local universe. A well-known example is the Virgo cluster. It lies at a distance of tens of millions of light years. This distance is much larger than the size of the local group. It represents a step outward where the million light-year scale becomes tens of millions. The Virgo cluster contains many galaxies, including giant ellipticals, spirals, and dwarfs. Its galaxies are spread across a region several million light-years in diameter, with a denser core and a more extended outer region. The cluster's gravity binds these galaxies together despite the overall expansion of the universe on larger scales. Cluster environments affect galaxy evolution. As galaxies move through the hot intracluster medium, they can experience ram pressure stripping, where the pressure of the hot gas removes cooler gas from the galaxy. This can reduce the galaxy's ability to form new stars. Tidal interactions and gravitational encounters can also distort galaxies and remove stars into the cluster's diffuse light. Over time, clusters can build large central galaxies through mergers and accretion. These central galaxies can become enormous elliptical galaxies that dominate the cluster core. Around them, the cluster contains a mix of galaxy types influenced by their histories and by their interactions with the cluster environment. The scale within clusters is still dominated by emptiness, but less so than in groups. Galaxies are closer together in clusters than in the field. Typical separations can be hundreds of thousands of light-years rather than millions. Even so, direct collisions between stars remain extremely rare because stars are tiny compared with the spacing inside galaxies, and galaxies are still mostly empty space internally. When galaxies interact, their gravitational fields distort each other, triggering star formation bursts or rearranging gas and stars. Over time, repeated interactions can transform spiral galaxies into more featureless forms. These are slow, cumulative effects with timescales of hundreds of millions to billions of years. Hot intracluster gas is a major scale feature. Its temperature can reach tens of millions of degrees Celsius. At these temperatures, atoms are ionized and the gas emits X-rays through processes such as Bremsstrahlung radiation, produced when electrons are deflected by ions. The gas fills the cluster volume and carries much of the cluster's ordinary matter. Its presence also reveals that clusters are deep gravitational wells. Gas that hot would escape if the gravity were not strong enough to hold it. The fact that it remains bound is evidence for the cluster's large mass. The gas distribution can also show substructure indicating mergers between clusters or groups. Clusters grow by merging with smaller clusters, and by accreting groups and galaxies along filaments of the cosmic web. The spatial scale of clusters also introduces another perspective on size. A cluster can span several million light-years. This means that light takes millions of years to cross it. Events in one side of a cluster are separated from events on the other side by delays of millions of years in terms of signal travel. Yet the cluster is bound, meaning gravity maintains the overall coherence. The gravitational field is a global property of the mass distribution, and changes propagate through the motion of matter and through the structure of space-time, but for most practical evolution, clusters evolve slowly compared with light-crossing times. Their large size and mass make them slow-changing structures that persist over long cosmic intervals. Clusters are also used to probe the universe's large-scale properties. Because their mass distribution and number density depend on cosmological parameters, their abundance and evolution over time provide constraints on the growth of structure. Their gravitational lensing effects can be measured to map dark matter. Their hot gas contains information about baryonic physics and feedback from galaxies. Yet within this script, the focus remains on scale. Clusters show that the universe contains structures far larger than single galaxies, and that these structures are bound and massive. The step from the local group to clusters is also a step from a sparse family to a dense environment. In the local group, the Milky Way and Andromeda dominate a few million light-years, with relatively few large galaxies. In a rich cluster, hundreds or thousands of galaxies share a similar volume. The cluster's gravitational environment is stronger, the galaxy velocities are higher, and the space between galaxies is filled with hot glowing gas. This makes clusters prominent markers in the cosmic landscape. By completing this region, the ladder has reached a scale where individual galaxies are many and close within a bound system, and where the distance measure is tens of millions of light-years to the nearest major clusters. The next step outward will move from clusters to the arrangement of clusters and groups into the cosmic web, the large-scale pattern of filaments and voids that spans hundreds of millions of light-years and sets the distribution of matter on the largest observable scales. From galaxy clusters as the largest bound islands, the next region expands to the cosmic web, the large-scale pattern formed by matter across the universe. The cosmic web is not a single object. It is a connected arrangement of filaments, sheets, clusters, and vast voids. It emerges from the growth of tiny density variations in the early universe under gravity shaped by the expansion of space and by the properties of dark matter and ordinary matter. At this scale, distances are measured in tens to hundreds of millions of light-years, and the notion of structure shifts from a bound system to a pattern that extends across enormous volumes. The cosmic web can be understood as a consequence of gravity acting on an initially nearly uniform distribution of matter. In the early universe, matter is distributed with small fluctuations in density. These fluctuations are measured indirectly in the cosmic microwave background as tiny temperature variations, which correspond to density variations. Over time, denser regions attract more matter, growing denser, while underdense regions become relatively emptier. Because the universe expands, the growth of structure competes with the stretching of distances. In regions where gravity is strong enough, matter collapses into bound systems like galaxies and clusters. In other regions, expansion dominates, and matter thins out. The result is a web-like pattern, dense knots where clusters form filaments connecting these knots, and large voids between them. Filaments are elongated regions of higher density that can span tens to hundreds of millions of light-years. They contain galaxies and groups aligned along their length, and they also contain gas and dark matter. Sheets are flatter regions like walls that can also host galaxies and connect to filaments. Voids are large regions with low galaxy density. They are not completely empty, but they have far fewer galaxies and less matter than the filaments and knots. Voids can be tens to hundreds of millions of light-years across. Their size is one of the clearest signals that the universe's structure extends far beyond clusters. The gaps between the densest structures are not small. They can swallow many clusters in volume. The cosmic web is mapped through galaxy surveys. By measuring the positions and redshifts of millions of galaxies, astronomers build three-dimensional maps of the distribution of matter traced by galaxies. In these maps, the web appears as a network of filaments and clusters. Redshift provides distance information in an expanding universe, though converting redshift to distance requires a cosmological model and can be affected by peculiar velocities, the motions of galaxies relative to the expansion. Even so, on large scales, redshift is a powerful measure of depth. The resulting maps show that galaxies are not randomly scattered. They follow the web's pattern with large empty regions and connected dense regions. The cosmic web is not only traced by visible galaxies, much of its mass is dark matter. Dark matter collapses and forms the scaffolding of filaments and halos. Ordinary matter falls into this scaffold. Gas can be heated as it flows into filaments and clusters, creating warm-hot intergalactic medium that is difficult to detect directly because its density is low and its emission is faint. Some of this gas is detected through absorption lines in the spectra of distant quasars and galaxies, where the intervening gas leaves a signature at specific wavelengths. These observations suggest that a significant fraction of ordinary matter resides in diffuse structures along filaments. This means that the web is a real mass distribution, not merely a pattern of bright points. At this scale, the universe's expansion becomes central to how distance is interpreted. Galaxies on very large scales show a general trend of recession, with redshift increasing with distance. This is the Hubble flow. The cosmic web sits within this expanding background. Filaments and voids are carried apart by expansion, while within dense regions gravity can resist expansion and form bound structures. The web is therefore a pattern in comoving coordinates, a way of describing how matter is arranged relative to the overall expansion. In such coordinates, the web's large-scale pattern remains recognizable over time even as physical distances increase. The scale of the web can be expressed in terms of light travel time. A distance of 100 million light-years corresponds to light traveling for 100 million years. This is long compared with human history, but short compared with the age of the universe. It means that when observing a filament at that distance, the observer sees it as it was 100 million years ago. Over such time, galaxies can evolve, star formation rates can change, and interactions can occur, yet the large-scale positions of clusters and filaments change slowly. The web structure evolves over billions of years, growing more pronounced as matter continues to fall into filaments and clusters. The observed web at different distances therefore reveals different stages of this slow evolution. Voids are especially important for the sense of scale because they represent vast emptiness. A void can be so large that light takes tens of millions of years to cross it. Within a void, the density of galaxies is low, and the gas density is also low. This does not mean voids contain nothing, but it means that most of the universe's volume is in underdense regions rather than in dense knots. The universe is therefore not mostly filled with galaxies. It is mostly empty space with matter concentrated in thin filaments and nodes. This is a structural reality, not a metaphor. The volume fraction in voids is large. The cosmic web also includes superclusters, loose associations of clusters and groups connected by filaments. Superclusters are not always gravitationally bound as a whole. They are large features of the web rather than single-bound objects. Their definition can depend on thresholds and mapping methods. A supercluster can span hundreds of millions of light-years. The local group and the Virgo cluster are part of a larger region often described as the local supercluster, historically called the Virgo supercluster. More recently, larger-scale mapping suggests even broader structures, where flows of galaxies and mass define extended basins of attraction. The exact naming is less important than the principal clusters and nodes in a larger network. At this stage, the ladder has reached a point where individual objects become less distinct and patterns dominate. A single galaxy cluster can be described as an object with a boundary and a mass. A filament or supercluster is less like an object and more like a connected region. Its edges are not sharp, its shape depends on density thresholds, yet it is still physically meaningful because it reflects where matter is concentrated. The web is the universe's skeleton on large scales. The cosmic web is also essential to understanding the farthest light, because it sets the distribution of galaxies whose light reaches the observer. Beyond certain distances, the web continues, but the appearance changes because the universe was younger. Galaxies were less evolved, and the distribution of matter was less clumped. At very large redshifts, the web structure is present but in earlier form. This transition will be addressed later in the script's outward to inward progression toward the observable boundary. By completing this region, the scale has expanded from clusters of tens of millions of light-years to a web of hundreds of millions, with voids and filaments defining the large-scale arrangement of matter. The next step outward will define the observable universe's radius in terms of how far light can travel since the early hot state. Introducing the idea that the farthest light is not simply the farthest distance in space, but the farthest distance in time that can be observed, given the universe's age and expansion history. From the cosmic web of filaments and voids, the next region is the observable universe's radius, the scale defined not by the reach of gravity or by the extent of matter, but by the limit of what can be seen, because signals travel at a finite speed, and because the universe has a finite age in its current form. The observable universe is not the entire universe. It is the portion from which light or other signals have had time to reach the observer since the early hot beginning. This region is defined by horizons by expansion, and by the fact that distance and time are linked in an expanding spacetime. To define the observable radius, two ideas must be held together. One is look-back time, the time a signal has been travelling. The other is comoving distance, a way of describing separation that factors out expansion by referring to coordinates that expand with the universe. If a galaxy is observed with a look-back time of billions of years, the light has travelled for billions of years, but the galaxy is not at a distance equal to that number of light years in a simple way. While the light is travelling, the space between the galaxy and the observer expands. The path length increases. The relation between travel time and present-day distance therefore depends on the expansion history of the universe. This is why the observable universe's present-day radius is larger than the age of the universe in light years. The age of the universe is on the order of 14 billion years. One might expect that the farthest light could have travelled no more than 14 billion light years. Yet when the expansion of space is accounted for, the present-day distance to the most distant observable regions is larger, on the order of tens of billions of light years. The commonly cited value for the radius of the observable universe is about 46 billion light years in comoving distance. This means that the most distant matter whose light can reach us today is now about 46 billion light years away, even though the light has been travelling for roughly 13 to 14 billion years. The difference arises because the universe was smaller when the light was emitted and has expanded during the light's journey. This is not a trick of language. It is a measurable consequence of cosmology. The expansion is observed through the redshift of galaxies and through the cosmic microwave background. As light travels, its wavelength is stretched by expansion, shifting it to longer wavelengths. This redshift encodes information about how much the universe has expanded since the light was emitted. By measuring redshift and applying a cosmological model consistent with observations, distances can be inferred. The model includes parameters such as the Hubble constant, the matter density, and the dark energy density. These parameters determine how expansion rate changes over time, and thus how look-back time relates to comoving distance. The observable universe is centered on the observer. Any observer anywhere would have their own observable universe, a sphere defined by their location and the finite speed of light. This does not imply the observer is special. It reflects the fact that observation is limited by causality. The boundary is not a wall in space. It is a horizon in time, the edge of what can be in causal contact with the observer since the early universe. The farthest light that reaches us today comes from regions that are seen as they were when the universe was very young. These regions are not seen through individual galaxies at the absolute earliest times, because early on the universe was filled with hot plasma that scattered light. Photons could not travel freely because electrons and protons were not yet combined into neutral atoms, and free electrons scattered photons efficiently. This early plasma state makes the universe opaque to light. As the universe expanded and cooled, it reached a time when electrons combined with protons to form neutral hydrogen. This process is called recombination, though it is the first combination in this context. When neutral atoms formed, the scattering decreased sharply, and photons could travel long distances. The light released then has been travelling ever since, stretched by expansion into microwaves. This is the cosmic microwave background. It comes from a surface of last scattering a shell around us at a very large distance and a very early time. The cosmic microwave background provides a direct observation of conditions when the universe was about a few 100,000 years old. It is not the earliest possible signal in principle, but it is the earliest light that can travel freely to us. It therefore defines a key part of the observable boundary in electromagnetic radiation. Beyond that time, the universe is not transparent to light. Signals from earlier times require other messengers such as neutrinos or gravitational waves, which interact less with matter and could in principle carry information from earlier epochs. Those are more difficult to detect and interpret, and they do not currently provide a full image comparable to the cosmic microwave background. The microwave background remains the most complete all-sky map of the early universe's state. The observable radius is therefore tied to two limits: the age of the universe and the transparency of the universe to light. The farthest light from galaxies is limited by when the first luminous source is formed and by the absorption and scattering of light along the way. The farthest light in a fundamental sense is the cosmic microwave background which comes from the time when the universe first became transparent. Beyond that, the observable universe in light does not extend, not because space ends, but because light cannot carry information from earlier times directly. The scale of the observable universe also includes the concept of the particle horizon, the maximum comoving distance from which particles, including photons, could have travelled to the observer since the beginning. The particle horizon corresponds to the boundary of the observable universe. Its radius grows over time because as the universe ages there is more time for light to travel. However, because expansion continues, the relationship is not linear in time. In addition, the universe's expansion is currently accelerating due to dark energy, which affects the growth of horizons. This introduces another horizon concept, the event horizon, the limit beyond which events occurring now will never be able to influence the observer in the future because expansion carries them away too fast. This will be treated in the next region, but it is foreshadowed here only as a conceptual link, not as a preview of details, because the observable boundary already depends on expansion history. To make the observable radius tangible, it can be compared to the Milky Way's size. The Milky Way is about 100,000 light-years across. The observable universe's radius is tens of billions of light-years. The ratio is hundreds of thousands. The Milky Way is a small speck in this sphere. The local group is smaller still. Even the cosmic web, mapped over hundreds of millions of light-years, occupies only a small portion of the observable radius. This shows that the web continues far beyond what is mapped locally, filling the observable sphere with patterns of matter at many scales. This region ends with the observable universe defined as a horizon-limited sphere, whose radius in present-day co-moving distance is far larger than the universe's age in light years due to expansion. It clarifies that distance to the farthest observable regions is not equal to light travel time in a simple way, and that the earliest observable light is the cosmic microwave background from the time of recombination. The next step outward within this outer to inner progression will refine the notion of horizons, distinguishing the limits of what can be seen now from the limits of what can ever be seen or influenced given the accelerating expansion of the universe. From the observable universe's radius as defined by light travel time and expansion history, the next region is cosmic horizons, more specifically the limits set by the way space expands and by how that expansion changes over time. A horizon in cosmology is not a physical edge. It is a boundary and causal connection defined by what signals can reach an observer, or what signals an observer can send that will ever reach something else. Different horizons describe different limits. The most relevant here are the particle horizon, which defines the size of the observable universe, and the event horizon, which defines the ultimate limit of future communication and observation in an accelerating universe. The particle horizon is the boundary already described the farthest distance from which light has had time to reach us since the early universe. It depends on the age of the universe and on the expansion rate over time. The particle horizon grows as time passes because light has more time to travel. However, the rate at which the particle horizon grows is influenced by the expansion history. In the early universe, expansion was rapid but also decelerating due to matter and radiation. As the universe expanded and thinned, the relative importance of matter and radiation changed. Later dark energy became dominant, and the expansion began to accelerate. This sequence affects how the horizon grows and how distances relate to redshift. The event horizon is different. It concerns the future rather than the past. It is the boundary beyond which events occurring now will never be able to send a signal that reaches the observer at any time in the infinite future. In a universe where expansion accelerates strongly enough, there are regions that recede from us so quickly that light emitted now from those regions will never overcome the expansion and reach us. This does not mean the light stops or disappears. It continues to travel locally, but the stretching of space between the source and the observer outpaces its progress toward us. As a result, those regions become causally disconnected in the future. The event horizon therefore sets a limit on what can ever be observed, not only what is observable now. To understand this without relying on metaphor, it helps to treat expansion as a change in the scale factor, a parameter that describes how distances between comoving points change over time. Comoving points are locations that move with the overall expansion, such as distant galaxies that are carried by the expansion on large scales. When the scale factor increases, the proper distance between comoving points increases. Light travels through this expanding geometry. The question of whether light from a distant source reaches us depends on the integral of the expansion rate over time. If expansion decelerates, light can catch up from farther away. If expansion accelerates, there can be a limit. In the current best description of the universe, expansion is accelerating due to dark energy often modelled as a cosmological constant. This acceleration means that there is an event horizon at a finite comoving distance. Objects beyond that horizon, if they emit light now, will never be able to affect us in the far future. Objects within that horizon can still influence us, though their light may be increasingly redshifted over time. The existence of an event horizon is therefore a statement about long-term causal structure, not about present visibility. It is also important to distinguish between recession speed and local motion. In cosmology, distant galaxies can have recession speeds greater than the speed of light, when defined as the rate of increase of proper distance due to expansion. This does not violate relativity because it is not motion through space at a local point. It is the expansion of space between points. Locally, no object moves faster than light relative to its immediate surroundings in the usual sense. Yet on large scales, expansion can increase separations faster than light can traverse them. This is one reason horizons exist. It is also why the present-day distance to a region can be larger than the light travel time in years. The Hubble radius is another related concept defined as the distance at which the recession speed equals the speed of light at a given time using the Hubble parameter at that time. The Hubble radius is not exactly the same as the event horizon or the particle horizon. It is a scale that changes over time as the expansion rate changes. Light can cross the Hubble radius depending on how the expansion rate evolves. In a decelerating universe, the Hubble radius grows, and light emitted beyond it can eventually reach us. In an accelerating universe, the behavior differs. The Hubble radius can approach a constant value in certain models, and the event horizon becomes a more stable limit. The key scale lesson is that multiple distance scales exist, and each is defined by a specific relationship between expansion and signal travel. For an observer measuring the farthest light, these horizons matter, because they explain why the observable universe is not simply a sphere whose edge recedes at the speed of light. The particle horizon defines what has already reached us. The event horizon defines what will ever reach us. Because the universe has accelerated expansion, there are regions that are currently observable in the sense that we can see light they emitted long ago, yet which are now beyond our event horizon in the sense that light emitted by them today will never reach us. This can happen because their earlier light was emitted when they were closer, and when the expansion conditions allowed the light to make progress toward us, while later expansion carried them farther away. The difference between past emitted light and future emitted light becomes essential. The cosmic microwave background sits near the particle horizon in terms of look-back time. It represents the earliest light that can reach us because the universe became transparent at that epoch. The event horizon does not change where that background comes from in the past. It changes what regions of the universe will remain observable in the far future. In an accelerating universe, the observable region in terms of incoming light from newly emitted sources can shrink in practice because distant galaxies fade from view as their light is redshifted and their signals become weaker. Over extremely long time, only a local set of gravitationally bound structures may remain visible, because everything else will be redshifted beyond detection and carried beyond causal influence. This statement is about the structure of horizons and redshift, not about intention or meaning. The scale of the event horizon in current cosmological models is on the order of a few tens of billions of light-years in proper distance, though the precise value depends on the cosmological parameters used. The important point is that it is finite and comparable in magnitude to the particle horizon, but not identical. The particle horizon is larger because it includes regions whose past light has already had time to reach us. The event horizon can be smaller because it limits future communication in an accelerating expansion. This relationship is one of the most counterintuitive aspects of cosmic scale, but it follows from the expansion history. In this region, the universe's size is therefore described not only by a distance number, but by limits of causality. The farthest light already received defines one boundary. The farthest influence possible defines another. Both are rooted in the same physics, the finite speed of light and the changing expansion rate. Both require the use of co-moving distance and proper distance carefully, because the meaning of how far depends on whether one is talking about distance, now distance then, or distance in expanding coordinates. This region ends with horizons clarified as time and causality limits rather than physical edges. The particle horizon sets the current observable universe. The event horizon sets the ultimate limit of future signal exchange and future observation in an accelerating universe. With these limits defined, the final region will move to the farthest light itself as an observational record describing the earliest electromagnetic signals that can be detected, what they reveal about early conditions, and why that light defines the deepest reachable boundary without extending into speculation beyond what can be observed. From horizons as causal limits in an expanding universe, the final region is the farthest light itself as an observational boundary, the deepest electromagnetic record available, and the way it sets the practical limit of seeing. The farthest light is not defined by the most distant galaxy image alone. It is defined by the earliest time when light can travel freely through space to reach an observer. That earliest freely travelling light forms a nearly uniform background across the sky, carrying small variations that encode the conditions of the early universe. It is the cosmic microwave background, and it arrives today after a journey of nearly the entire age of the universe, stretched into microwaves by the expansion of space. In the early universe, matter is hot and dense. Temperatures are high enough that electrons and atomic nuclei do not remain bound as neutral atoms. Instead, the universe is filled with a plasma of free electrons and ions along with photons. In such a plasma, photons scatter frequently off free electrons. This scattering prevents photons from travelling long distances in a straight path. The universe is therefore opaque to light not because it has walls, but because the mean free path of photons is short. The photons are trapped in a scattering environment, exchanging energy with matter and remaining in thermal equilibrium. In this state, light does not carry a clear picture across large distances. It is like a dense fog in the physical sense of repeated scattering. As the universe expands, it cools. Cooling happens because expansion increases the volume and reduces energy density. Eventually, temperatures fall to a level where electrons can combine with protons to form neutral hydrogen. This transition reduces the number of free electrons dramatically. With fewer free electrons, scattering becomes rare. photons can then travel long distances without being scattered. This moment is called recombination, and it occurs when the universe is on the order of a few 100,000 years old. From that time onward, the universe becomes transparent to radiation in most wavelengths, and the photons released then travel outward in all directions. Those photons fill space. An observer today receives them from all directions as a background glow, because the universe has expanded enormously. Since recombination, the wavelengths of these photons have been stretched from visible and infrared wavelengths into microwaves. The background is therefore observed in the microwave band with a temperature just a few degrees above absolute zero. The spectrum is close to that of a blackbody, indicating its origin in an early thermal state. The small deviations from perfect uniformity are the most important part for understanding structure. They are tiny temperature differences across the sky, corresponding to slight density and velocity variations in the early plasma. These variations are the seeds from which later structure grows under gravity. The cosmic microwave background is often described as coming from a surface of last scattering. This is a useful geometric idea. It means that the photons an observer receives today last scattered off matter at a distance corresponding to the particle horizon at the time of recombination mapped forward by expansion. The observer sees a sphere because photons arrive from all directions. The radius of that sphere in comoving coordinates is large, comparable to the observable universe's radius. The light has been travelling for more than 13 billion years, but the comoving distance to the region that emitted it is tens of billions of light years today because of expansion. This is the farthest light in a practical sense, because earlier photons could not travel freely. The microwave background is not entirely featureless. Its anisotropies, the small variations, have a characteristic pattern of angular scales. These scales reflect acoustic oscillations in the early plasma waves, driven by the competition between gravity pulling matter inward and radiation pressure pushing outward. The resulting pattern is imprinted in the temperature fluctuations. By measuring these fluctuations precisely, cosmologists infer key parameters of the universe, including the curvature of space, the relative contributions of ordinary matter, and dark energy, and the scale of initial fluctuations. These inferences are not arbitrary. They arise from comparing observed patterns to the predictions of physical models that include well-tested plasma physics, gravity, and expansion. There are also secondary effects imprinted on the background as the photons travel through the evolving universe. As the photons pass through gravitational potential wells and hills, their energies can shift slightly, and as they pass through hot gas and clusters, they can gain energy through scattering. These effects provide information about structure at later times. Yet the primary message of the farthest light is that it is a snapshot of the universe, when it first became transparent with tiny variations that encode initial conditions. The farthest light from galaxies in the sense of light emitted by stars comes from later times, because stars and galaxies form after the first few 100 million years. The earliest galaxies observed are seen at very high redshift and represent an early phase of star formation and assembly. Their light has also been stretched into infrared wavelengths. Observations with powerful telescopes can reach very early galaxies, but these galaxies do not define the ultimate electromagnetic boundary because they are later than recombination. They are embedded within the already transparent universe. They are part of the record between the present and the last scattering surface, not the deepest boundary itself. The farthest light sets a limit on what can be observed with electromagnetic radiation. It does not mean nothing exists beyond. It means that electromagnetic photons cannot carry a direct image from earlier times because the early universe was opaque. In principle, other messengers could provide information from earlier times. Neutrinos decouple earlier because they interact weakly, and gravitational waves can propagate through matter with very little interaction. Detecting a cosmic neutrino background or primordial gravitational wave background is extremely challenging, and present observations provide constraints rather than direct images. For the purpose of defining the farthest light, the electromagnetic boundary remains the cosmic microwave background. This final region also closes the scale ladder from Earth outward. Earth is a sphere measured in thousands of kilometers. The Moon is hundreds of thousands of kilometers away. The Sun is 1 astronomical unit away with light travel time of minutes. The outer solar system reaches light travel times of hours. The nearest stars are light years away. The Milky Way spans 100,000 light years. Nearby galaxies are millions of light years away. Clusters in the cosmic web extend to hundreds of millions of light years. The observable universe reaches tens of billions of light years in present-day distance. The farthest light is the cosmic microwave background, arriving from a boundary set by transparency in the early universe and by the finite travel time of photons through an expanding space-time. The real size of the universe that can be described by observation is therefore not simply a maximum distance number. It is a combination of distance, time, and physical conditions that set where light can travel. The farthest light is an ancient signal uniform in its broad glow and patterned in small fluctuations marking the deepest electromagnetic view. It is the limit of looking outward, because beyond it in time the universe does not allow light to carry a clear record to the present.